Howdy. This is what I believe will be the last of the recordings with actual new material in them for the semester. So we've made it very close to the end now. In the video today, I'm going to talk about variations on reactions in sequence. As you know, in most reactions, we have a mechanism that consists of some series of steps. And today we'll look at some of the possible ways that we can handle those things, what are really some limiting cases on how the rate laws work out and the like. Before we start into that, I put in here at the beginning another question that might have been a clearer question if we were in class. This one is relatively straightforward. I'm confident I've used this one in my Chem 107. It says there are two reactions plotted on what is a sort of classical Arrhenius plot over there, log of rate constant versus 1 over temperature. It asks which reaction has the higher activation energy. Okay. There are a couple ways you can go about answering that. The simplest way is to remember that the slope of that graph in the Arrhenius plot is minus E sub A over R, where E sub A is the activation energy. That means the steeper slope is the one that has the larger activation energy. And so that means what? That means it needs to be B. That's a pretty simple question for us, I hope. You can do that by working with equations and stuff, but it's a lot easier just to think of the graphical connotation. All right, venturing into a series of reactions now. One starting point for this is just to think about reactions that go into equilibrium. When we teach mechanisms in general chemistry level, for example, we say that if the slow step is not first, then the steps earlier than that generally can be thought of as going into equilibrium. Equilibrium itself is a thermodynamic idea, right? It's the eventual outcome of things. It's related to delta G, all of which point to its being a thermodynamic quantity in a sense. But the way we get to equilibrium, of course, is governed by kinetics. Lots of reactions never make it near equilibrium if the rate constants aren't right for that to happen. A simple case, the simplest possible case, would be an equilibrium that's a single first-order elementary reaction in both directions. An example of that might just be an isomerization, something like converting cis and trans isomers of something where you have to break the double bond and rotate it. That should be a one-molecule process in either direction, and we should get, depending on the temperature, some split between the two things being at least the equilibrium mixture. In that case, it's pretty easy to write down the stuff that's on there. So K1 is the forward rate constant, K minus 1 is the backward rate constant, as indicated by their positions here on the arrows. If I do that, the rate of change of the amount of A, K1 times concentration of A, this is a loss of A, so that's a minus sign in front of there. K minus 1 times concentration of B, that recreates A, so that's a positive term in our rate expression there. If I take that thing, that change in concentration has to be 0 at equilibrium, right? That's one definition of what it means to be at equilibrium, is that concentrations are no longer changing. That says I can take the two terms there and set them to be equal. So I can write this equation, which if I rearrange it, essentially gets me an equilibrium constant, right? A concentration equilibrium constant Kc, where B is the product, right? So this is the products over reactants expression over here. And we can also say that equilibrium constant should be equal to the ratio of the two rate constants, K1 over K minus 1. So the forward over the backward rate constant is another way of putting that. We can take that idea, and sometimes we use that to put together rate laws or expected experimental rate laws for things, I guess I could say. An example here is reaction between NO and H2. There are a lot of reactions like this that take place in the atmosphere, and so there's lots of kinetic data on all sorts of reactions involving various nitrogen and oxygen compounds. That's why they tend to show up as examples in a lot of kinetics chapters in chemistry texts, at least. A possible mechanism for that is written out down here. The label's the slow and fast steps here, right? So this points to arguments like the rate determining step that we talk about in Gen Chem, where we say the rate of the overall reaction should in general be set by the rate of the slow step. We're going to dive into that a little bit in this video and explore the extent to which that's true and the limits in which that's totally true. So this is the case that should happen if k minus 1 is a lot bigger than k2, right? That's what makes the first step be fast compared to the second. Saying the second step is slow or rate determining says that k2 is small, because that's what leads to a slow reaction number 2, right? So that says if I asked my freshman class to write a rate law for this thing, after teaching them about the rate determining step, they would go to this step here, and they would say the rate of the reaction should come from that step. All right, which means that one is tempted to write down K2 times the concentrations of N2O2 and H2 for your rate law. If you do that, and if you say this is the overall equation up top, and this is the rate law, then what happens is you have a rate law that has in it the N2O2, which is neither reactant nor product. What that means in practical terms is that you would not be able to use that rate law in most cases to figure out what the rate of reaction would be. Right? If I told you I want you to start this reaction with this concentration of NO and this concentration of H2, and I gave you that rate law and asked you to tell me the rate, you would look at me and say, well, I didn't put any N2O2 in the reaction mixture, so I don't know how to use that equation to get a rate for it. Right? That's because the N2O2 is an intermediate here. If we flip back to our mechanism, right, we create it. That's really strange, it didn't go on there. We create the N2O2 here in the first step, and then we use it up in the second step, right? So it is not reactant nor product. It is neither, it doesn't show up on either side of the final equation for the reaction. So in order to make this rate law more useful, we would like to eliminate the N2O2 concentration from it. So we have something that only has reactants and or products in it, right? We can do that using the fact that our first step went into equilibrium. Since we know about equilibrium constants, I'm going to write it out this way instead of in terms of the balance of the rates, but we could say that this equilibrium constant for step number 1 should look like that, right? Where that's the product over the reactants raised to powers, just like a normal equilibrium expression. We can solve that for the N2O2, the intermediate concentration, which gives us this form over here, right? Lastly, then, I'm going to take my Kc times NO2, or NO squared there, and I'm going to bring that up, and I'm going to stick it into the rate law there in place of the N2O2. When I do that, I get the rate law down here, which says that, at least in terms of apparent kinetics, in terms of the reactants, this looks like a third order reaction, right? So as a third order rate law, it does not, you will see, you can see from the mechanism, involve any 3-body collisions. That's actually true for a lot of third order rate laws. We think of that as meaning that we have a third order step for the rate determining step, or a ternary reaction. That actually is rarely the case. There's some debate among people that study kinetics in like molecular level detail as to whether or not there are any reactions that really take place due to 3-body collisions. But if there are, they're very rare. Okay, a number of things that used to be thought of as being 3-body collisions have now been experimentally shown to be 2 sequential things, just with the sequence being very fast. Nowadays, experiments to look at things like that can be done on timescales down getting close to 10 to the minus 15 seconds. And so the evidence is growing that there's probably not any substantial number of 3-body collisions, which is essentially just because molecules are fast and small, right? And so having a pileup of these fast, small things is very unlikely, and because the actual collision doesn't last long. They come together, they collide, they do what they're going to do, and they separate, and that whole process is very fast. Consecutive reactions is what I think I put as the, I put sequential reactions maybe on the posting of this stuff for this, but same idea. Lots of reactions involve a series of consecutive steps. We can think about this as being a mechanism. We can think about them as being separable reactions where we can see each one happen. One field in which lots of things go this way is radiochemistry, the decay of radioactive material. Right? There are many things where if we get far away from stability, we go through a cascade of processes to work our way back towards more stable nuclei. And so a relatively simple one on the bottom there is uranium-239 decaying to neptunium-239, which decays further to plutonium-239. The times written up there, those are half-lives for these things, okay? So those are the half-lives for the 2 steps. meaning that here my first step is noticeably faster than my second step, according to those numbers, right? The rate laws for these reactions are coupled to one another, right? So what we get if we try to put together the rate expressions for this is we get a set of coupled differential equations. The reason for that is the first reaction produces the source for the second reaction, right? So I can't start the decay to plutonium until I've made the neptunium, right? In this case, because the neptunium, the half-life of the uranium isotope is the short one, that suggests that we probably will end up building up some neptunium because we should be making the neptunium faster than we're using it up. Okay, and we'll see how that works out in the equations as we go through an example of this. I'm going back to A, B, and C here, just because frankly it's simpler than typing in the isotopes and whatnot for all that, but we could in the end go back and think about this as telling us about that particular decay chain if we wanted to. So what I've got is I've got A goes to B with a rate constant K1. I've got B goes to C with a rate constant K2, where the 1s and 2s just label the sequence or the steps in sequence in my mechanism. Rate law for the first step is simple, right? And I'm saying these are both, we're writing these as first order processes because we're trying to keep this relatively simple. So my first reaction just says change in concentration of A with respect to time is equal to minus K1 times concentration of A, right? That just says this is a first order decay. B is the more interesting one, right? Because B is being produced and it's being consumed, right? So it's got a source, which is the first term here, K1A. That's positive because that's increasing the concentration of B. And it's got a sink, which is minus K2B over there. That term is negative because that's diminishing the supply or the amount of B on hand, right? And then lastly, once I've made B, then my second step can kick in and I can make C. And so the rate for C depends only on the concentration of B, at least directly only on B. It does depend indirectly on what's happening with A because that feeds into how much B there is, right? So that gives us the set of equations. They're linked because I have the B terms and the various rate laws appearing in more than one equation there. The simplest one to start with is just the first reaction, the concentration of A. That one's just going to be an exponential decay, right? Because it is being consumed in a first order reaction. As written, our mechanism has no way to provide for reforming A. That would be true, at least in the case of those radioactive decay chains, for example, right, where those reactions are pretty thoroughly non-reversible. I do not go backwards up those things because I'm going downhill in nuclear stability, where the energy changes are quite large for that, right? So that gives me a very simple equation for what's happening to the concentration of A. If I look at B, it is a more complicated situation, let's say, right? I have the rate law there, which says that dB dt is this expression. We wrote that on the previous slide. Now I have this one for A. If I take that second equation for A and put it into the B equation, then I can do a little bit of rearranging and I get an expression that looks like the one on the bottom here, right? So this says the concentration of B depends on both rate constants, K1 and K2, and it depends on the initial concentration of A because that's what drives the later time concentration of A. If you look at the form of that equation, it means that what should happen is that the concentration of B should go through a maximum and then decay. That more or less has to happen because it's the intermediate species, right? So I start making it, in the beginning I have no B present, so it's got to go up initially, right? If I let this reaction go for infinite time, presumably if everything's just going forward, I end up with only C being present, right? That suggests that B has to go up and through a maximum somewhere along the way, and that equation says it would in fact do that. As long as the stoichiometry is even all at 1-to-1, then we can also say that at any given instant, the concentration of all three things added together is equal to the initial concentration of A. That would be true again for my radioactive decay example that I started out with because I make one atom of each isotope as I go along, right? So the total number of atoms that I had in that example would always be the same. Right? That would be true for anything as long as I'm in this 1-to-1 ratio. If you do that, and I'm going to pop up the worked out argument for this in a second, but it's possible to show then that from where we are for A and B, we can get an equation for C, which is the one that's down there on the bottom, which relates the concentration of C at any time t to, again, the two rate constants and the initial concentration of A, because those are the things that are in control, right? If I know the two rate constants, initial concentration of A is the only other thing I get to pick, right? I get to pick a temperature, but that's essentially just what sets the two rate constants. I did slap in some slides here to look at how we get from where we were on the last slide to that equation on the bottom, because I will say, when I went back through these, I thought, well, it's not obvious at all that it comes out to be that. So here goes a little bit of substitution. This is going to be probably a little quicker than it would be in live class, but you can always pause and work through it. And I'll post the version of this in the slides as well. So the top is just my equation for the concentration of A. This one is the equation for the concentration of B, right? We had those two before. This is the added wrinkle here that says that I'm setting the stoichiometries all 1-to-1 so that the total concentration is constant. Right? If I sum the three of them, it's always the same as the original A0, because originally B and C are both 0. Take that and rearrange it to get an equation for the concentration of C there, right? And then into that, we're going to put A0. So this A0 comes from here. Then we're going to put A, which is this piece here. That is the concentration of A. Where that's coming from this equation up here, right? And then this one, this last term, all of that stuff is this, just with the A0 moved to the front. So that just says I took the things we already had and I put them all in there, which gets me an expression which has in it the two rate constants and A0 along with the time. From there, we just have to do some simplifying to get to the one that I showed before. And this is a lot going on this slide, so take a moment and go through it. The top line is just where we were when we left the bottom of the previous slide, okay? In this line, all we've done there is factor out an A0 and pull it to the front, right? Because in the top line, all of my terms have A0 at the front of them. This just takes that out in front, multiplies it through. In the next term, what we've done is we've got this K2, the K2 minus K1 denominator here, right? So I take that first term, this term, I'm going to multiply that on the top and the bottom by K2 minus K1. When I do that, I get the expression as written there, right? Which says I get the top there. You have to be careful with the signs here, but they should all work out. And then on the bottom, I just get a K2 minus K1 for that as well. Then in the next one, all we've done is we've taken this K1 and distributed it through to make it show up in those two places, okay? Once I've done all that, if I actually do the subtraction of the two terms that are over K2 minus K1, I get this line, and the two pieces that I, in the slides, just went ahead and drew the lines through, those two will cancel, right? So my two terms in the middle here will cancel one another. That leaves me with the expression on the bottom, which is the one that I offered up as just a declared result before that. Okay, so it says, this is more complicated, right? Mathematically, it's more work just because, well, the equations are now chained together, but it's nothing that's that terrible to do, and it gets us a result for what should happen. If I take that expression and look at it in limits, I can think of the rate limiting step argument, basically, which says that the fast step doesn't matter and the slow step is in control of the overall rate, right? If K1 is much smaller than K2, then the K1 in the bottom essentially goes away, right? Then I get to say up top that, again, my K1 piece is negligible, and I end up saying that I get, wait, hang on a second. I missed that. Yes, right. In that case, my K1 piece on the top is negligible as well, and my result simplifies to this one, right? Which says that in that case, K1, which is the slow rate constant, right? It's the small one, so it's the slow step is the only rate constant that shows up in my equation for C. That's the rate determining step argument, right? Go the other way around. K2 is now the small rate constant. So K2 is the slow step. Then it's the K2 term that goes away out of there, okay? And when I do that, I'm left with the expression below, right? So this says that I have K2 as I have the K, K2 is the small one. So I neglect the K2 in the bottom, and that reduces down to being this piece, okay? Sorry, I'm back. I took a brief pause in the recording there because something was going on. So this shows us that we can make the same arguments that come from the rate determining step, which is just the simple way of saying this. We can justify those by actually looking at the set of differential equations that drive things through there, right? It's possible, of course, to get into the case where we're not at either one of those limits, where the rate constants could be comparable to one another, and then we'd have a more complicated set of kinetics for which we could actually use the equations we just worked out here and get a much better model of things than we would by trying to impose the notion of a rate determining step. Because although most reactions do have something that can decently be regarded as a rate determining step, there's not a requirement that that be true. We could have a sequence of reactions that had the same rate constants, essentially, and then we'd have to do this the harder way. These are a couple of just sets of plots made for this, and I guess I know for a fact that things like this go on in the Chemi kinetics class that some of you are in concurrently typically. And so on the left-hand side, labeled as A, we have the K1 is the big one, so step 1 is fast, step 2 is slow. And what happens in that case? If we look at what's going on here, in this graph, my A concentration goes down sharply because K1 is big, step 1 is fast. My B, my intermediate concentration, builds up to a rather high level because that says I get lots of B made, and then it takes its time decaying, right? So the rate of decay of B is small because K2 is small, and that means the rate at which C grows in is relatively slow, right? So it takes me a while to get my C rising up here. On the right-hand side, we have the opposite limit, right? So my rate constants here are differing by a factor of 10, it looks like in either case, right? So both of those have K1 set at 1, and K2 is either a factor of 10 smaller or a factor of 10 larger. When step 2 is fast, in that case, I don't get much B building up, right? So if I just look at B down here, step 2 is fast, which means essentially just about as soon as a B appears, it gets sucked through the second reaction and comes out as a C. So there's never a lot of B present in that circumstance. Right? In this case, it takes longer for the A to go away, right? If I look at the slope of the decay of A, it's going more slowly because, well, I'm not clearing the stuff out of there as fast, right? And so it is definitely taking its time going down. If you look at the plots here, oh gosh, that's strange. I didn't even notice that. The decay of A shouldn't be changing, and it's not changing, right? Because it's just going through its one step. What happened is that I accidentally plotted my graphs, or wherever I copied these graphs from, they have different x-axes, which is kind of awkward. So the fact that it looks like A is going down more slowly is not really true, because if I come out to the 4-second point here and to the 4-second point there, we can see that it looks like I'm at about the same amount of decay, which I should be because I didn't change the rate constant for K1. And so those are actually the same plot for concentration of A. It's just the other parts that are changing. My B and C are definitely changing, right? If I look at C in this case, I've got pretty much 100% conversion to C after 5 seconds. Over here, if I come in at 5 seconds, I've got less than halfway there, right? Because the left-hand side is with a slow reaction to, the right-hand side is with a fast reaction to, in which case I get to my final product that much more quickly. It's odd that I didn't notice before that those axes were different. Oh, I put in a second question here, which I forgot all about, so I'll have to read it as we're doing this. Reaction is between hydrogen and bromine to make HBr. It's a nice, simple-looking reaction, right? H2Br2 makes 2 HBr, so we're just trading partners there. The rate law for this thing is rather awkward-looking. It has the expression written there experimentally, right, where it's 3/2 order in the Br2. It's got dependencies on the H2 and the Br2, and even the HBr gets into the act in the rate constant there because the mechanism for this is rather involved. And so what does it say? It says, which of the following is true? The rate constant is always 3/2 order in Br2. It's always 1/2 order in Br2. Or it's got different things going on at different times. Okay, so let's think our way through this, I guess. If I look at this, the always 3/2 order or always 1/2 order, those don't look right, I think, because they look like I have, I have the 3/2 power up here, and so, but then I've got a first power of the bromine down there. When it says initially and later, we have to think about what's going on. The thing that's changing there is mainly that we're getting HBr, right? So initially there's no HBr. And so initially, at the start of this reaction, my second piece here, the K2 HBr in the denominator, that is 0 when I start the reaction. And what that means is that initially that says I could take the Br2 in the bottom and cancel a Br2 from above. And that one says it's definitely 1/2 order in Br2 initially, right? If my reaction is almost done, then eventually the concentration of HBr is bigger than the concentration of Br2, right? So at long times, the term that's got the lines under it here, this one dominates and this one disappears. When that happens, then it becomes 3/2 order in bromine at longer times, right? So that's an example of what happens over the course of a reaction, changing what the observed rate law would look like, because there's a lot more going on in the kinetics than is apparent from the reaction itself. The last thing I'm going to mention in this video is a quick word about the steady state approximation, which again is something I'm confident has got to come up in your kinetics class that you take in your department. The steady state approximation is really a way of getting to at least one case of the result we've looked at with a simpler argument instead of doing the fully coupled equations, right? It says intermediates in reactions are often highly reactive and therefore short-lived things. Think about the number of reaction mechanisms that say something like first step involves generating a free radical of some sort. Maybe it's an oxygen atom, something like that, right? And then the next step involves that free radical going on to react with something. That free radical species is going to be very reactive, right? If you've got an oxygen atom that somehow you've split off from anything else, oxygen atoms don't like to just exist by themselves, right? If you built up a significant number of oxygen atoms, if there was nothing else to do, they'd stick together and make O2s, right? So we know we can't build up a large concentration of something like O atoms. So the intermediate is going to be reactive and therefore short-lived. So this is the case where we're saying that the second step, the step that uses up my intermediate, is going to be fast, right? Steady state approximation says that the rate of concentration of the intermediate does not change over most of the course of a reaction. So mathematically, that says we can write something like this, where the intermediate there just represents whatever species it is that's made in the initial step and then used up in the subsequent step. So we can say that the rate of change of that substance should be 0 over most of the course of the reaction. It's not going to be true at the beginning and the end, but for long times in the middle, it should work itself out that way. And if we do that, we can do the following bit of equations, right? So up top, I've got my overall scheme, same as before, just K1 for the first step, A to B, K2 for the BC second step. This line here is just the same set of, these are the rate laws for, or the rates expressed in terms of the different components there. Steady state approximation says I want to set dB dt equal to 0 because B is my intermediate, right? It's the thing that I make and then use up. dB dt from up here is equal to that expression. So here I just set that equal to 0. If I do that, I can rearrange and get this expression there, right? Take that, and I can say that my dc dt from over here, which is equal to k2b, k2b from this one, if I just multiply k2 over there, k2b is also equal to k1a, right? So I can express dc dt in either of those ways, according to this. If I take that, then I take the equation for the concentration of A, right, which just says A is just decaying exponentially. It's its initial concentration, e to the minus k1 t. So I can express my C concentration directly in terms of the initial concentration of A then. That gives me this rate law here. If I do that, from there, I can separate my variables and integrate. That amounts to just saying I'm going to get concentration of C on the one side. So I'm going to leave the D concentration of C where it is, multiply the dt to the right, integrate that side, and the result is this, okay? That's the same equation we got when we did the actual coupled equations thing. This is a bit of a simpler route to get there, I think we can agree, right? It didn't involve that multiplying everything out and canceling all those terms. We effectively did that when we set the derivative of b equal to 0 and made that steady state approximation, right? And so that gives us a shorter route to there for the limiting case where the intermediate species is reactive. So that's where the second step is the fast one, and the slow step is first, so that my intermediate concentration stays small and stays fairly flat throughout.